right, hello everybody. Welcome back to Easy Math with Nick. Today we are on big video number 20. And today we are going to be doing AP Physics C FRQ from 2019. Specifically, this is electricity and magnetism now. I'm happy to do this one because I just finished learning Unit 8, or the first unit in the electricity section of AP Physics C curriculum. So I am now able to do this free response question with you guys today. So what better way to start our 20th video together. So this is from the 2019. I just said that. So you can find this online for your own perusal. So, okay, let me read the question, as always. A very long, thin, non-conducting cylinder of length L is centered on the y-axis, as shown above. The cylinder has a uniform linear charge density, positive lambda. Point P is located on the y-axis at y equals c, where L is much greater than C. So L is much greater than this distance here. Okay, on the figure shown below, draw an arrow to indicate the direction of the electric field at point P due to the long cylinder. The arrow should start on and point away from the dot. So, okay, when we look at the net electric field at point P, we have to consider the figure that they gave us here. So point P is on the y-axis, and there's an equal amount of charge to the left here as to the right. So the rod is, as they said, centered on the y-axis. So half of the rod's on the left, the negative, the second quadrant there, and other half is on the right. What that means here, and as it has a linear charge density too, that plays a factor. If we look at the electric field due to, let's say, a tiny bit of charge there, it's going to be up in that direction, right? Because it's positive, and we assume our test charge is positive, right? That's the convention we go by. Now, if we look at, let's say, on the other side here, a little bit of charge, it's going to cause an electric field in that direction. So if we were to integrate, if we were to work out the math, we would see that for every pair of little charges on the rod like this, the x components go in opposite directions. You see that? So they're going to cancel out. So there is not going to be a net electric field in the x direction at point P. Instead, as we see here, the similarity between these two electric fields caused by the two little charges I made there, the little like segments of charge that I indicated, is that the y components are both in the positive y direction. So we're going to only have an electric field in the positive y direction. So it's going to be an arrow straight up. And that is our net electric field at P. So I'll call it EP. Okay, that was pretty, wasn't so bad, right? Similar to drawing a free body diagram in mechanics. So a lot of the same skills carry over. Now they want us to describe the shape and location of a Gaussian surface that could be used to determine the electric field at point P due to the long cylinder. So you're taught that there are three types of Gaussian surfaces that you can utilize. That being spheres, cylinders, and planes. Well, or not necessarily planes, but how do I put it? The other one. Well, whatever. I'm not here to explain all the other ones that we're not using. Let's focus on the one we are using, which is a cylinder. We would use a cylinder here because I'm treating this long cylinder as essentially just a rod with not much height. So if we have the rod there, and we draw a cylinder, it's going to be a very badly drawn cylinder, sorry, but pretend the cylinder is engulfing the entirety of the rod. The electric field, when we look at the end caps, is going to be 0 because, I'm sorry, let's concern ourselves first with the electric flux, sorry. The electric flux at the end caps is going to be 0 because when we look at the dot product of E and area, let's say dA because it's a little bit of area, it's going to equal 0 because they're both parallel. There's no they're both perpendicular. dA is what? It's going outside of the it's parallel, perpendicular to the surface, and then we have the electric field from the rod going up. So that's going to equal 0. So but at every other point, in order for Gauss's law to apply, at every other point the electric field must be constant, and that's true because we're each a radius r, whatever we choose, away from the surface, so the electric field is going to be constant. And because the rod is the bar is very long, compared to our radius that we have on our gouging surface, it's going to remain constant. So Gauss's law will apply here. So we would use we would use a gouging surface of a cylinder that's centered on the x-axis so that it envelops the long rod. So that's part I. I won't write that out. I think I'll just I think my words will be sufficient. And now for part I. Use your gouging surface to derive an expression for the magnitude of electric field at point P. So let's go ahead. So as I might have already mentioned, we're going to be using Gauss's law here. This is a Unit 8 problem, so I chose it specifically because I have the knowledge to use it. So the surface integral of the dot product of E and the dA, which I already briefly explained, is going to be equal to the enclosed charge over E naught. So if we look, because we chose this surface wisely, the electric field at each point on the surface is going to be either 0 or constant. So we could pull E out of the integral there because it's a constant. We'll just have the surface integral dA equals, well, what is our enclosed charge, right? They don't give us that, unfortunately, right? But we could deduce that. So if we look at lambda, which is our uniform linear charge density. So lambda is equal to the net charge over the length, which is Q over L. But they don't tell us the net charge of the very long thin non-conducting cylinder, right? They don't tell us that. So instead, we're going to have our answer in terms of lambda, which they want us to do. So instead, because lambda is a constant, and by the definition of lambda, it should equal Q enclosed over some smaller length L that we're going to be looking at here. So the enclosed charge could be rewritten. I shouldn't have used L because L and lambda are sort of similar, but I'm only using script L to show that we're not dealing with the entire length of the non-conducting cylinder. The very long is very long, so L is quite a big number, quite a big quantity. We're just looking at a smaller segment of it for this problem. So for this case, although there's nothing stopping you from actually, I think never mind, because then we'll call this big L. Because we still don't know the enclosed charge anyway. Whatever, forget everything I was saying. Let's just use big L. There you go. You do want to use big L here. I don't know what I was thinking. Because we want to enclose the entire rod to find the electric field at P. So disregard everything I mentioned. It won't matter anyway for as you might see. But we're going to do that. So we just substituted that in here. That's all we did. And now the surface integral of dA is going to be no, we're not dealing with the 2 pi r. What is our radius? C. So 2 pi c, because r equals c here, right? Because if we look at our graph, this distance here is equivalent to c. And that's what they want our answer in. So that distance is a distance c. That's why they give that to us. L, which is the length of the long rod, and therefore the gouging surface that also is enclosing the rod, going to equal lambda L over E naught. So not too much nice cancellation here, but the L's do cancel. So even if we use little L, doesn't really matter. But I don't think that's technically the way you want to look at it. But I think that's our answer. So if you check our units, lambda is charge. The units are newtons. Wow, coulombs over meters. So you're gonna have coulombs over meters squared, because C is a length of C is a quantity of distance, and then E naught is where it should be. So our units check out. That's our answer for part I. Not so bad, right? Okay. Let's move on to part B. A proton is released from rest at point P. On the axis below, sketch the velocity as a function of position y and the acceleration as a function of position y. Okay, so we know the electric field, even the electric field is equal to um, electrostatic force on an object divided by the charge of that object. So, therefore, the electric field, which is lambda over 2 E naught, equals, well, now it's not going to be C, right? Now it's going to be something greater than C. So we'll call it R, or we'll call it Y, is equal to ma over q. Force equals mass times acceleration, Newton's second law. We know that from last year. So now we'll do our acceleration graph first. But as we increase, as our position y gets greater, which means we're going from y equals c to, let's say, y equals 3c up here, or 2c, whatever. As that gets bigger, the acceleration is going to decrease and approach 0. So if we're starting at c here, we're going to start our graph here. It's going to show a downward curve like that. That's expected of like a 1 over c relationship, or 1 over x relationship. So it's going to take like that downward curve. I didn't draw it so well, but I think you get see what I'm getting at there. And now when we look at the velocity graph, something similar is going to happen. Because the acceleration is approaching 0, velocity will be approaching a constant value. So we'll also see a curve, and it's starting at point C, but it will be curving upward until it reaches some constant velocity. By the point where we're so far away from the rod that the electrostatic force, as dictated by Coulomb's law, becomes essentially negligible. So it's the proton's only going to be pretty much at a constant velocity. So that's why the graphs are the way they are. Okay, so now things get interesting. The original cylinder is now replaced with a much shorter, thin, non-conducting, I think it was also non-conducting before, that doesn't change anything, cylinder with the same uniform linear charge density, positive lambda, as shown in the figure below. The length of the cylinder to the right of the x-axis is A, and the length of the cylinder to the left of the x-axis is B, where A is less than B. Okay, so now instead of being centered with respect to the y-axis, as it was previously, that was part of explanation for part I, or my explanation. They didn't ask you to explain, as why there's only a vertical component. Here, that's not the case anymore. Here, there's more charge on the left side here than the right side. So when we look at our electric field at point P, there's more charge, there's more positive charge on the left pushing, acting on our test charge that we would place at point P to find the electric field. So the electric field is going to be going up and to the right. So that is the main difference here, because the x components no longer all cancel out. Because if we look, I'll just do a little example here. Okay, if we look at, say, a little charge here, it could be pushing, it will cause an electric field in that direction. And on the opposite side, it would cause an electric field in that direction. Great. But now, for every one of those that cancels out, there's more on the left side that don't, and cause a net electric field in the positive x direction. So you have to, that's how you deduct that the y component, that there's not just only a y component now, there's also an x component to the electric field at point P. So that would be your arrow that you would draw there. Okay, I can move this up a little bit. Is there a single Gaussian surface that can be used with Gauss's law to derive an expression for the electric field at point P? I'll spoil it. The answer is no. You cannot use a Gaussian surface here, because now something important that they tell you here is a much shorter non-conducting cylinder. Before, it was a very long, thin non-conducting cylinder, and that was important as to why we could use Gauss's law, right? Because in that example, if we looked at each point on the surface of our Gaussian surface cylinder, the electric field is constant, and that's why we're able to pull the electric field out of the integral. That's how Gauss's law applies for that scenario. Here, the rod is much shorter, and if we were to draw a Gaussian surface, if we were to attempt that, if we looked at each individual point on the cylinder, the electric field will not be the same. It would vary, because the distance. I'm sort of explaining this right now, but the distance from the center of the distance from the radius of the cylinder, essentially the distance from the center of the cylinder to its surface, is no longer negligible compared to the length of the cylinder. We're no longer at a point where the length is much, much greater than that radius. So we can't say anymore that the electric field would be constant. And Gauss's law would not apply here, because that our conditions for when we would use Gauss's law is not met. To show this mathematically is a little bit difficult, so I went for more qualitative description. Hopefully that got the point across. I'm trying to see if there's another way I can explain that better. I might come back to that, but the answer is most certainly no for that. They made that explicit by saying that the cylinder is much shorter, which you would, if they didn't tell you that, you would just have to make an educated guess. But okay, I'll move this up now, because there wasn't much work for that last one. Okay, a student in class argues that the integral shown below might be a useful approach for determining the electric field at point P. Okay, so this is not even using Gauss's law. This is just application of Coulomb's law now. The student uses this approach and writes the following two integrals for the magnitude of the horizontal and vertical components of the electric field at point P. So the horizontal component is that ugly thing. And then the vertical component is that. Okay. One of the two expressions above is not correct. Which expression is not correct? Okay. So just eyeing this right now, I'm leaning towards the vertical not being correct, because I don't know why they have things in terms of dy. Y isn't changing. Y is a constant. So I don't know why they have it like that. So I would say the vertical component. But let's find what the vertical component actually is, so we can correct the mistakes correctly. Correct them correctly. Whatever, not the best way to put it. But okay, so let's look at the let's look at the rod. This is y equals c, point P. So if we're looking at the electric field at point P, let's first, yes, give me a second here. Yeah, so we have looking at a certain dq, a certain little bit of charge at a position x on the x-axis, causing an electric field at a certain angle. So if we want to, do we want to use the and we'll call the shear distance r, and x would just be the position on the x-axis. That's the best way to go about this. Okay, so if we set up our integral, e equals, I'm trying to just see what types of variables they used. R is going to be that distance from the charge, the little bit of charge dq, to that point P. X is just going to be the distance on the x-axis at that point dq is located, the charge dq is located at. And I just used the angle theta there because that's going to be helpful for the finding. So if dq is equal to lambda dx, because lambda is a constant, and we already explained what lambda is before, but that's where we would plug in dq, and r is equal to, I'm sorry, I think we want, okay, yes, we're looking at the vertical component here, so we would need a sine theta. That's my bad. I shouldn't have forgotten that. Okay. Well, this is why we do this, because sine theta is going to equal y over r. So if we want to substitute that in, we could also do that as well. And now we need a substitution for r. By Pythagorean theorem, x squared plus y squared is going to be equal to r squared. R is going to equal radical squared plus y squared. And y is just a constant, right? Y is not changing, so we'll rewrite when we go to plug this into our integral 4 pi I'll replace y with c, because y is not changing. That's why I think this is wrong, because dy doesn't really make sense, because y is a constant. I don't know why they would include that. So, I don't know why I took the square root if I'm just going to square it again, but whatever. Then we'll have, I don't know, because we also kind of need to plug this in there too. Oh, I was supposed to replace y with c. No, I said I would do that. I lied to you. Well, now at least I could get rid of square root, so I'll have x squared plus c squared. And we'll have dq, which is lambda dx. And times sine theta, which is going to be y over c, not y, c, right? I don't know why I'm making this more complicated for myself. X squared plus y squared. Now, finally, if we clean this up, we could pull lambda, c, and 4 pi e naught outside the integral. Yes, we could do all of those wonderful things. So what that's going to look like is we're going to have c over lambda c over 4 pi e naught integral. And this will be vertical component will be from negative b to a. The limits they had were right, but the limits they have are quantities on the x-axis, not the y-axis, which just shows again why dy is not correct. But I'm just showing what is correct, just so if you were so inclined. C squared to the 3/2 dx. Because c is a constant, we can pull it out of the integral. So I'm pretty sure that is the actual integral for the vertical component. But it seems that, oh, they did use y. Okay, but y is a constant. Oh, that, so maybe that's why subconsciously use y. Okay, but the two mistakes are that there's two clear mistakes there. They're using y instead of, they're using dy instead of dx. dy, dx, I'm sorry, dx used instead of dy because limits of the integral are x-axis distances. Doesn't really make sense if our limits have to do with the x-axis, but we're integrating with respect to dy. That's just kind of confusing. And also, so that's number one. Number two is, if you look here, it's not to the power 3/2 plus x squared term should be to the half power. Yeah, so that was something those are two mistakes that they would change. And how to correct the mistakes, just instead of to the first power, have it be to 3/2. How you should change the mistake for dx, well, I would replace dy with dx. And if you make those two changes, you're going to get the right answer, because you would have y equals c, and c would come out of the integral, and then you would have exactly what we got here. So those are the two mistakes that they had in part E. So I think that's it for this free response question. The last part, there's a lot of work that I was doing here. If you didn't follow what I was doing, don't be too concerned with it. You could even get the same result I did just by comparing these two and looking at and realizing that the first one is the one that's correct, and that the second one doesn't have the 3/2 power, which why doesn't it have that? It should, and that it's integrating with respect to dy, which just doesn't make sense. So you didn't have to go through all the work like I did, but I just wanted to show what the right answer would be, just in case you were curious. But that's it for this problem. My graphs look pretty good. They're just sketches. After all, they don't have to be perfect by any means. So that was AP Physics C 2019 FRQ, specifically for the electricity and magnetism exam. And that's video number 20. Thank you for sticking with me. Next video will be, I don't know what next video will be, but it'll be coming up somewhat soon. Hope you enjoyed this one. It was fun to do an electricity magnetism FRQ for the first time with you guys. And I look forward to the next video. See you then.